Swayam Prabha. Digital India. Educated India.
Welcome to the lecture on linear algebra. In this lecture, we are going to look at some of the hands-on examples in linear algebra. We are going to take a quick look at the recap of how to create matrices, what are the common matrix operations. We are also going to take a look at how to find the determinant, how to find the inverse of a matrix, and how to transpose a matrix. Followed by that, we'll take a look at how to solve a system of linear equations, and we will also look at how to find the eigenvalues of a given matrix. Now let's see how to create a matrix. To create a matrix, you can use the function matrix. Now it takes the set of numbers that you want to give. The set of numbers that you are given can either be a sequence or it can be different number that has been combined using the function c. And after that, you need to give the number of rows, number of columns. Now the parameter by row basically takes the value true or false. If you give it as false, which is also the default value, it arranges all the elements column wise. Otherwise, if you give it as true, it arranges all the elements row wise. So let's run the function. Now if you print a and b, you can see that the corresponding elements have been arranged row wise, and this is the output that you get. So the first matrix operation is addition. So corresponding elements of the two matrices are basically added, right? Similarly, you also have subtraction, where you subtract the two matrices and the corresponding elements are subtracted. So there are two ways to go about multiplication. One is element wise and the other is a dot product. So in element wise multiplication, the corresponding elements in both the matrices are multiplied, whereas in dot product, what happens is the first row of matrix A is multiplied with the first column, and that's how you generate the resultant cells of the new matrix. So division is always element wise. You basically divide the corresponding elements. Now let's take a look at accessing elements from a matrix. So if you want to access the first row and the second column, then you give it like this, and you have matrix A. Within square indices, you basically give 1, 2. The index before the comma represents the row and the index after the comma represents the column. Let's say you want to access all the rows from the second column, then in that case I need to leave the position before comma empty, and I just need to give the second position alone, which is the column. In this case it's 2, because I want to access all the rows from the second column. So if you want all columns from the second row, then you need to leave the column space empty, and I'm just filling only the position before the comma, and I'm filling it as 2, which denotes the second row. Let's look at a sub-matrix selection where I have a condition on the rows and columns. So I want all the rows to be displayed for columns 1 and 2. So when you want all the rows, you can give 1, 3. And since I want column 1 and 2, I'm just giving 1, 2. So all rows from the columns 1 and 2 get printed. So this is the sub-matrix that you get. Now let's say if instead of having continuous rows, you just want to print the first and the last row and the first and the last column. So in this case, I'm printing the first and the third row and the first and the third column. So in that case, you can use the C function and just give the column names and the row name. So this is the corresponding output that you get for this condition. So now let's see how to delete a specific row or a column. So to delete a specific row or a column, you can just add a negative sign just before the index. Now let's say if I want to drop the second column, I just give the column number and I just negate it. So this drops the second column, and similarly you can also do it for the rows. Now one thing to note here, that all of these operations that we've done, we've just displayed them. We have not updated in matrix A. So if you want to update it in matrix A, then you can just give A equal to the following operation, or you can also generate a new matrix saying some other matrix notation equal to this operation that creates a new matrix with the updated changes. Now let's look at how to calculate determinant. To calculate determinant, you need to use the function det. Now you can give det of A. A is the matrix here. So this gives you basically the value of the determinant. Now in this case, you will see that the determinant value is very less. It's 6.6 into 10 power minus 16. Now whenever the determinant value is 0 or very close to 0, then in that case the inverse does not exist, right? So for inverse to exist, the determinant should not be equal to 0. So to find the inverse of a matrix, you can use the function solve and within parentheses give the matrix name. So in this case, it throws an error saying system is computationally singular. So this basically is because the determinant is almost equal to 0, right? It's still not exactly 0, but it's almost closer in the vicinity. So, and that is the reason the inverse function does not work here. But if you have determinant not equal to 0, then this function will completely work. It will give you inverse of the matrix. Now let's see how to transpose a matrix. To transpose a matrix, you can use the function T. It basically swaps the rows with the columns. Now to find the rank of a matrix, you need to load the package Pragma. If you have not already installed it, you can go to the packages tab here and install the package. Now you need to load the library before you use the rank function. So you can load Pragma by using the function library. So I'm creating another matrix A here. So this is the matrix. You can print it and see what the matrix looks like. And to find rank, I'm using the rank function. It is a function with a capital R, right? And once you find the rank, you can see that the rank function is 2, which means there are 2 linearly independent rows or columns. In this case, from the matrix, it's clear that the second row is twice the first row, and hence you can only see 2 independent rows, and that's why the rank is 2. Now we started with 3 rows and we have the rank as 2, which means we have 2 linearly independent rows, right? So in that case, the null space is 3 minus 2, which is equal to 1. So to calculate the null space, you can use the function null space or null, and you can just give the matrix within the parenthesis. Now null space basically tells you the number of relations which lie in the null space of the matrix A. And in this case, let's see what the value is. We have only one relation in the null space. So this tells you that there's only one relationship for the matrix A, and that is also true because rank is 2. So when rank is 2, the number of equations for your matrix can only be 1, right? And that equation, we basically find it from the null space. So let's look at how to solve a system of linear equations. We are going to be taking 3 cases. The first case is m equal to n, the second case is m greater than n, and the third case is m less than n. Now m equal to n basically tells you that the number of equations and variables are the same. And the second case, which is m greater than n, basically an equation where you have more equations compared to the variables. The third case is m less than n, when you have more variables compared to the equations, right? So let's look at each of these cases individually. Now the first example that we have is for m equal to n, and in this case I'm defining 2 matrices. One is A and the other is B. What we would like to solve is Ax equal to B. So this is how the system of equation looks. Now let's compute the determinant of this matrix. If you look at the determinant value is equal to minus 2, and let's compute the rank as well, and the rank is 2. So when you have the rank as full, it means you have 2 linearly independent rows or columns, which is also equal to the dimension. So in this case, the rank is full. What we also see is that the determinant is equal to minus 2, which is not equal to 0, and therefore the inverse for this matrix exists. Now why do we need to calculate the inverse? We need to calculate the inverse because we have the system Ax equal to B. X is an unknown, so we are basically trying to solve x is equal to A inverse B. So when you're trying to solve x equal to A inverse B, you basically need to find the inverse and multiply it with B. So to find the inverse, like I already said, you can use the function solve and then multiply it with the matrix B. So once you solve this, you will get your unknowns. Your value of unknowns are 1 and 2. So let's look at the second case, which is m greater than n. Now for both this case and the next, where one of the either the equation or the variable is greater than the other, so it's going to be difficult to solve for unknowns. For both the second and the third case, we are going to use an optimization approach, which is called pseudo inverse. Now let's take the second case where m is greater than n. In this case, you have more equations compared to the variable, right? So let's create the 2 matrices A and B for this example. So we are going to use the function pseudo inverse for this, and this is basically the optimization perspective. So we are going to first load the library mass and then use the function G inverse of A and then multiply it with B. So G inverse of A is basically gives you the pseudo inverse, and then you can use that to multiply with B. So the G inverse function also gives you the same output as you would get with this equation. So instead of using all the transpose and the multiplication and the inverse, you can directly use the G inverse function that gives you the pseudo inverse for this system. And once you run the function, you can get the values of x. So let's just print the values of x here. And even for this system, the value of x is equal to 1 and 2. Right? Now let's look at the third case, which is the infinite solution case. Now in this case, you have more variables compared to the equations, and this is again going to be difficult to solve. So again, we are going to use an optimization perspective here. And similar to the earlier case, we are again going to use G inverse, and that would give you the same result as what you would get using this equation here. Like I said, instead of using this whole expression to calculate it, we can just use the function to get the output. So let's use the G inverse function to solve this system of equation, and let's print the value x. And even in this case, the value of x turns out to be 1 and 2. So now let's look at eigenvalues. Now to look at eigenvalues, I'm creating a new matrix called A with these values. It has elements 8, 7, 2, 3 arranged row-wise. To compute the eigenvalues, you need to use the function eigen and give the matrix as an input. Now I'm saving this under the variable name EV. Now EV will have two values. One is the eigenvalues and other is the eigenvectors. So to basically look at eigenvalues, you need to use EV $values. This gives you the eigenvalues. And to look at eigenvectors, you can use EV $vectors. So let's look at the values here. So let's print values and the variable vectors. Right. So here you can see that the eigenvalues are 10 and 1, and these are the corresponding eigenvectors. So you need to look at each of the column. The first column corresponds to the eigenvector for eigenvalue equal to 10. The second column corresponds to an eigenvector for an eigenvalue equal to 1. So this is how you get the eigenvalues for any given matrix, and eigen is the function that you will be using. It returns both the eigenvalues and the eigenvectors. So to summarize, in this lecture, we looked at a quick recap of how to create matrices, what are some of the commonly used matrix operations, and we also took a look at how to access the elements from a matrix. Then we looked at how to find the determinant and inverse of a matrix, and we also looked at how to transpose a matrix. Followed by this, we looked at how to solve a system of linear equations and how to find the eigenvalues for a given matrix. Thank you.